Okay, so to picture where the graph of a polar function comes from, it's helpful to consider the rectangular function that's the equivalent. So we're thinking about r equals cosine 2 theta. So I'm looking at y equals cosine 2x. And when x equals 0, when the rectangular, y equals 1. When theta equals 0, in the polar function, r equals 1. So the point A on the rectangular function corresponds to the point B on the polar function. Now we'll map out the polar function in slow motion. See, as just what's happening speaks for itself, I think. X on the rectangular function is corresponding to theta on the polar function. And it becomes quite obvious where the function comes from. And I'll just speed it up a bit to finish up. Okay. Now, as far as symmetry tests are concerned, I assume you would agree that this graph satisfies all three symmetries. It's symmetric with respect to the pole, the polar axis, not the pole, well, the pole also, but the polar axis, because these points up here reflect across the polar axis to these points down here. It's symmetric with respect to theta equals pi halves, because you've got points, these points reflect to these points. It's also symmetric with respect to the pole, because this point here reflects through the pole to this point here. Kind of similar to origin symmetry in rectangular. Now, you notice that this rectangular function is symmetric with x equals 0 because it's even. It's an even function. X equals 0 on the rectangular function corresponds to theta equals 0 on the polar. This function is also symmetric with respect to x equals pi halves, and so it's also, the polar is symmetric with respect to theta equals pi halves. Now, the exceptional one is the pole. The original function, the rectangular function, y equals cosine 2x, does not have origin symmetry. But the polar function does have pole symmetry. So let's check, see how the different tests, what the different tests are and why they work. So the test for, let me pause and copy this into Smart Notebook. Okay, if you're testing for symmetry with respect to the polar axis, you, if r negative theta is the same thing as, if you replace theta with negative theta and get the same, I'm going to write it this way. If you replace theta with negative theta, the original function is a function of theta. If you replace theta with negative theta and get the same thing, then you've got polar axis symmetry. Well, let me go back to so here when theta equals 0.42, to say, the positive value of theta gives you the same r value as the equivalent negative value of theta. That's positive theta gives you the same r as the equivalent negative theta. or the negative theta gives you the same r value. Negative theta gives you the same r value as theta. Negative theta and theta have the same r value. Okay? So this is polar axis symmetry. Now, let's show that this actually does have polar axis symmetry. So the function was cosine 2 theta. R of theta equals cosine 2 theta. Well, we replace that with 2 times negative theta. That's too sloppy. That's 2 times negative theta. Well, cosine 2 times negative theta is negative 2 theta. But cosine is an even function, so that's just the same as cosine 2 theta. In fact, any cosine polar function is going to be symmetric with respect to the polar axis because cosine is an even function. Now, how about with respect to the theta equals pi halves symmetry? Okay, well, that means that this r has to be equal to this r here. So this r is created from the input of theta. It has to equal the r at pi minus theta. Here's pi. Subtract theta, whatever it is, say like 10 degrees in this case. When theta is, let's say, pi sixths, theta r has to equal when theta is pi minus pi sixths, or pi sixths. So let's, so the test is r of theta minus pi minus theta has to equal r of theta. So we're going to replace cosine of 2 theta with 2 times pi minus theta. And that's the cosine of 2 pi minus 2 theta. And subtracting 2, okay, so cosine of 2 pi minus 2 theta. Because cosine is even, that's going to be equal to the cosine of 2 theta, minus 2 pi. That's the opposite. Opposite inputs on cosine give you the same output. And subtracting 2 theta from an angle, well, it's going to have the same cosine. So that's the same as the cosine of 2 theta. So the original function remains intact when replacing theta with pi minus theta. And finally, we have with respect to the pole. Well, one test for the pole is if you replace r with negative r, you get the same function. That tells us that any r squared equals, r squared functions are always going to have symmetry with respect to the pole. But if we replace r with negative r in this function, we're not going to get the same thing. However, there's another test for a pole. With respect to the pole means that this point should reflect through the pole to this point. So r of theta should equal r of theta plus pi. R of theta, well, I'm going to put it the other way. If we add pi to theta, theta plus pi, we get the same thing we had originally. And let's show that that's true. the cosine of 2 times theta plus pi. That's the cosine of 2 theta plus 2 pi. Sorry for the sloppiness. And that's, of course, equal to the cosine of 2 theta, because adding 2 pi doesn't change. Will give you the same cosine as you had before. And so we do have polar. We do have symmetry with respect to the pole here as well. All right, I hope that's a reasonable explanation.